Hello and welcome to the Satellite Motion video tutorial. Here we have a 860 kilogram satellite rotating around or revolving around the Earth, and we're going to solve for the amount of time it takes for the satellite to make one trip around the Earth. Before we even start, what we're going to do is take care of some astronomical data that we need. If you look at our picture, we have a satellite that is at an altitude of 2,000 kilometers, but we're going to end up needing to know how far the satellite actually is from the center of the Earth. So we're going to need to know the radius of the Earth. The way that you determine the radius of the Earth is that you just look it up. You can look it up on Google, or you can look it up in the front cover, back cover of a textbook. And the radius of the Earth is 6.3781 times 10 to the 6th meters. So that's the radius of the Earth. We're also going to need the mass of the Earth later on, so we might as well just get that now. The mass of the Earth is equal to 5.974 times 10 to the 24th kilograms. Alright, so first thing we're going to do after doing this is get our force diagram. So I'm going to look at the forces acting on our satellite. Well, we have the force of gravity pulling down on the satellite, G, and well, actually that's it. If you look at the satellite, you have gravity pulling down and there is nothing else acting on the satellite. So what we have is that the net force is equal to Fg. So this means that mass times acceleration is equal to our force of gravity, and our force of gravity is equal to G times m1, m2 over r squared. Because this is our force of gravity, and we're just setting that equal to ma because ma is the net force. Alright, so we need to figure out what these masses are. This second mass here is the mass of the Earth, and our first mass is the mass of the satellite. Next we're going to determine which mass this m is here. Well, this regards to the mass that is accelerating, and the Earth is not the thing accelerating, it's this accelerating around in a perfect circle. So this must be the mass of the satellite. Alright. So because this mass is orbiting around in perfectly circular motion, that means that this acceleration here is v squared over r, because that's the acceleration for an object that is moving in perfectly circular motion. Acceleration is equal to v squared over r. So we'll bring this side down here, right there. And now what we're going to determine is we're going to figure out what the actual r value is. So r is the distance from the center of the Earth to the satellite. So that's going to be 6.3781 times 10 to the 6th meters, plus our altitude, which is, looks like 2 times 10 to the 3rd, but that's kilometers, so that's actually going to be 2 times 10 to the 6th meters. 2 times 10 to the 6th. So 6.3781 times 10 to the 6th plus 2 times 10 to the 6th is 8.3781 times 10 to the 6th power. And that's meters. Alright, so looking at our equations over here, we can actually see that there are things that cancel out on both sides. So this mass over here will cancel out with this mass, and this r right here will cancel out with one of these two r's over here. So what you're going to be left with is v squared is equal to g times the mass of the Earth over r. Let's put times in there. So the velocity is equal to the square root of g times the mass of the Earth divided by the radius of the Earth plus the altitude of the satellite, the distance from the center of Earth to the satellite. All right. So v is equal to the square root of 6.67 times 10 to the negative 11th, because that's the gravitational constant, 6.67 times 10 to the negative 11th. That's what g is, times the mass of the Earth, which is 5.974 times 10 to the 24th. Divided by the radius, which is 8.3781 times 10 to the 6th. Whoops. All right. So our velocity is equal to, let's see, 6.67 negative 11 times 5.974 24 equals, divided by 8.3781 e6 equals this really big number, and I'm going to square root it, and I get 6.896.4 meters per second for my velocity. Alright, so that tells us the velocity of the satellite. That's the tangential velocity of the satellite. But we still need to figure out how long it's going to take for that satellite to go around the Earth. So we're just going to break this off so we can see that we're doing something new down below that. Alright, so the satellite's making one trip around the Earth, and it has a velocity, and that velocity is going to be the distance that that satellite travels divided by the time, because that's what velocity is, distance divided by time. The time is the time it takes to go one trip around. The distance is the distance around. Well, because the satellite is traveling in a circle, the distance is the circumference of that circle. So that is going to be 2 pi r divided by t. So rearranging this, that means that the time is equal to 2 pi r divided by v. So the time to make one trip around is equal to 2 pi times 8.3781 times 10 to the 6th divided by 6896.4. So figure that on the calculator. 2 times pi times 8.3781 e6 equals, and divided by 6896.4 is equal to 7633.135 seconds. So this is our answer here, but it's not very common to leave an answer in terms of like 7,600 seconds, because who knows what that is. So we're going to put it in something more familiar. So there are 60 minutes, or so 60 seconds in a minute. So I'm going to divide that by 60 to determine the minutes, and then I'll divide that by 60 again to determine the number of hours, because there are 60 minutes in an hour. So that comes out to 2.12 hours for the satellite to make one trip around the Earth. Thank you for watching the Satellite Motion video tutorial.